Okay, thanks so much, Bob. Thanks, Dima. Pleasure to be here. Pleasure to be back at IPAM. Yeah, so the goal for me today is to give a really overview-ish overview. The first day of talks, we've kind of tried to get overviews. After that, it's a free-for-all. But I'm going to try to overview the entire meeting in the next roughly 45 minutes. And so we'll see how that goes. So what I tried to do was actually create a Venn diagram of the whole meeting. And it took me I worked for 2 hours trying to make a Venn diagram. And after 2 hours, I absolutely failed. And then it hit me I could do a word cloud. So I've done a word cloud. That is my Venn diagram. And my stalking horse is, let's go through it. And if we go through this, I boiled it down to, I think it was an 80-word word cloud. I took all the words from all the titles of the talks. I think I took the title of the meeting. Don't know if I put in anything else. And these are the 80 words it spit out. And so my hope is to chase through all these words and try to sum up the entire meeting for us and try to start some cross connections forming, which is the goal of the whole week. Okay, the two big ones, if you didn't notice, are rotating convection. Those came out pretty darn large. Next thing I noticed, can we lower these lights at all? Any chance? If we can, it'll help. Thank you. Awesome. So, next words that showed up before we get into rotating convection, I just thought I'd do numbers, parameters. Again, we got to be definitional first. So let's do non-dimensional parameters. Ratios of terms and equations, or of time scales or length scales, or what have you. I'll focus right here in this slide on time scales. So we have the rotation time, 1 over 2 omega. You'll see that as tau omega. We have some sort of advection time. That's the characteristic length over, again, some characteristic velocity. That's tau u. And then we have a viscous diffusion time, tau nu, where nu is the kinematic viscosity of the material, and kappa, so a thermal diffusion time, where kappa is the thermal diffusivity. And if we start playing with these ratios, we arrive at an Ekman number. You'll see that all week long. Ekman is essentially the non-dimensional rotation period of the system, and it ends up having this functional form. So if it's low, it means the rotation period is short. You have a rapidly rotating system. Okay, we have the Reynolds number. So that's the viscous time over the advection time. If the advection time is incredibly short, Reynolds is high, you probably have a turbulent flow of some form. If we take the timescale ratio of rotation and the advection time, then you get the Rossby number. So again, if this is short, then like Ekman, it means rotation is winning, right? It's the shortest timescale in the system. So for Rossby, this ratio is the multiplication of Reynolds and Ekman. And so a lot of what we'll be talking about today is whenever we're talking about extreme systems, we'll be talking about systems that probably have a high Reynolds but a low Rossby. Right? That's where, for me, the extremes are. That's where the action is. Geostrophic, rapidly rotating turbulence. That's these two. Okay, what else will we see all week? We'll probably see Rayleigh numbers come up. That's basically thermo-viscous diffusion versus, I've put it as an advection time, but here it's a buoyant advection time. And if we do that, we get this term here, alpha g, delta t is some sort of temperature difference across our system. Alpha is the thermal expansivity, g is gravity, characteristic length scale, and then our diffusivities. And so when that is large, we'll tend to get buoyantly driven flows. We'll get buoyant convection. And a lot of times what we'll talk about is the supercriticality of the system, which I'll denote Rayleigh tilde. And so that's what's the Rayleigh number relative to some value at which you get some bifurcation in the system. So the higher that is, the more strongly supercritical the convective flow. What else we got? We have the ratio of diffusion time, so essentially the material properties of the fluid. That's the Prandtl number. And another one we'll probably see a lot this week is the convective Rossby number, which you can think of as essentially a buoyantly fueled local convective scale Rossby number. It's a priori estimate of that value, and it goes as square root of Rayleigh-Ekman squared over Prandtl. It'll come up a lot. It shows up in many, many problems, and it's often one of the critical or the critical control parameter. We'll probably talk about heat transfer. That's the Nusselt number. Very roughly have argued it's roughly, it's not exactly this, but it's essentially the conductive heat flux divided by the time scale for the advective heat flux. And then the last two things that probably will come up multiple times are the geometry of the system. If we're doing cylindrical problems, we'll probably have the cylindrical aspect ratio showing up. I denote that gamma, diameter over height. And the other one that we'll see probably is a spherical radius ratio at times. I denote that a chi, inner radius of the shell over outer radius of the shell. So now we have the geometry. If we have an infinitely thin cylinder, so massive D, that goes off to infinity. In contrast, for the radius ratio, when you go to an infinitely thin shell, that goes to 1. So note they have different bounds. All right, so those are non-dimensional parameters. We'll see them all week. Great. Let's keep going through our word cloud. Let's focus on rotation for a minute. Rotation. Okay, so if we look at Navier-Stokes in a rotating reference frame, we have inertia, Coriolis, the pressure gradient, lab gravity, centrifugal, and some sort of viscous term. And let's just walk through it. Let's say we're in a system where U is 0. So then static balance is these three terms in the yellow ellipse. And so in this balance, we tend to get a level surface that's a paraboloid. So if I just rotate a tank, then I get the fluid coming to static balance as a paraboloid. And if we put a camera in the rotating frame, you can see I taped a camera right there. That's my cell phone. That's the view. And the minute I stop the rotation, I lose the centrifugal effect, and I go back to a flat level surface. But when I'm rotating, the actual equipotentials are not flat. So flat becomes a paraboloid. So if we want to then switch and worry about what are the motions from Coriolis, then we'll go onto this level surface and we'll launch a free particle. So let's launch a free particle. We'll say viscosity is weak. And in this case, we'll just have inertia versus Coriolis. And in this case, since Coriolis isn't directly injecting any power, it's simply deflecting off to the right, then we should get circles, right? That is the solution for that equation in purple. And so we can do this again on a record player. Here I bought a really cheap paraboloid. It's a little paraboloidal dish. I found the rotation rate. It was like 56 point blah blah RPM, at which it's an equipotential surface. So that's a flat surface in a rotating system. And if we launch a couple of free particles, we get these complex motions viewed in the lab frame. But if we transform to the rotating frame, because, sorry, let's see if I can do that again. My apologies. Maybe you can see, there's my camera again up there. So I have a camera in the rotating frame too. And if we do that, then we see we get circles, right? A free particle in motion stays in circular motion in a rotating frame. And if they run into each other, they stay in circular motion, right? If you have a collision, you still get circles. Okay, and you might say, well, wait, why'd those two stop? Yeah, because there's rolling friction. I said they're truly free, but there was some friction there. Still, that gets you the idea. So we've got our circles. Now let's go to convection. Okay, here's a device built by Jules Abate. it's a convection device, heated from below, cooled from above. She put a light in the back and an imaging plane on the front. So she's doing shadow graph here. And if we look at a non-rotating convection experiment, so 0 RPM, then we see these types of flows. This is a gamma 1/2 cylinder. It's distorted because we just put a single light source behind. But that's a right cylinder. And you can see these large-scale motions with lots of small-scale turbulence as well. That's a Rayleigh number of about 4 times 10 to the 11. So it's about 10 to the 8 times supercritical. And it's a silicone oil, so Prandtl's about 20. OK. Now let's finally add these things together. Now let's go to rotating convection. And now we'll do the exact same experiment, but now at about 76 RPM. So the Ekman number is now 6 times 10 to the minus 7. So the rotation period is much, much, much shorter than any viscous time scale. And we see a fundamental change in the flow. The flow is now on all these rather thin, rotationally aligned structures, which I'm sure we'll talk about all week. Maybe this is rotating turbulence. And sometimes you'll see people talk about quasi-geostrophic turbulence or geostrophic turbulence or rotationally constrained turbulence. That's roughly what we're looking at here. The Reynolds number is well over 10 to the 4. Rossby number is about 10 to the minus 2. So it's turbulent, but it's turbulence dominated by rotation. And one of our arguments is that our little lab cylinder can be ported to some geophysical system, image from Thomas Gastine, and maybe that applies. This is what we should be talking about all week. When does it apply? How does it apply? Does it actually scale? How does it scale? OK, and that leads me to scaling laws. We'll definitely be talking about scaling laws this week. For instance, amongst others, when I look at this, I immediately start getting really interested in what's the horizontal length scale. And so surely we'll have a lot of discussion. One end-member argument is near the onset of convection. The horizontal scale versus the vertical scale h should scale as Ekman number to the 1/3. OK, that's near onset. That's the critical estimate. That's the prediction. At the other end, if we go to the diffusion-free turbulent limit, we would argue that L over H should go roughly as the convective Rossby number, which we could rewrite as square root of the supercriticality over the Prandtl number, again, times Ekman to the 1/3. Very nicely worked out in Joukowsky 24. That's probably the clearest example of how to get to there. And people have actually been arguing about this for ages because it really matters. These can be much larger scales than this estimate. And so when we're talking about planets or stars, that difference can be huge. And so knowing what's actually living inside these systems, that's our job. And you might say, well, clearly they're rather different. No, it's not clear they're rather different. They both have Ekman to the 1/3. And if I'm doing experiments, laboratory, numerical, it doesn't matter, where this is not really big, then these look the same. And in fact, if I only do a couple of different Rayleigh numbers or supercriticalities, but then do different Ekman numbers, they'll look almost exactly the same, right? So that's troubling, and we should be thinking hard about that. Because if we're going to understand these equations, we have to know, in a sense, all the gradient operators, all the curls. If you can't even estimate the dominant scale, how do you move forward sensibly with those equations? This is huge. That make sense? So this one's really big. And we should be definitely working our way through that, fighting our way through that. Again, if we want to live in this asymptotic diffusivity-free regime, we have predictions for heat transfer. We'll surely talk about that this week. That roughly goes as Rayleigh or supercriticality to the 3/2. And if we estimate the velocity as a Rossby number, then in that same limit, you'd predict the velocity would then go as convective Rossby squared. I will point out one thing real quick. The measured Rossby number is Rossby, but the control parameter is often convective Rossby. Who did that? That's like the worst nomenclature in the world. We might want to fix that one of these days. But yes, this is a measurement, this is a control. Fine. Okay, just know it. All right. So rotating convection. Let's start going other places. What else is in our word cloud? Earth, planet, moon, icy. Great, let's do it. Fabulous. So for the geophysicists here, we have a number of people who study terrestrial bodies. There's Earth on the left. It's got, in addition to rich oceans and atmosphere, slowly convecting mantle, convecting on maybe 100 million year time scales. And then where most of the efforts of people in this room are is probably in Earth's outer core, where we have about a Mars-sized ball of liquid metal. Prandtl number's low, well less than 1. Ekman is about 10 to the minus 15. Reynolds is about 10 to the 9, 10 to the 10. Rossby is about 10 to the minus 6. So Reynolds is really high, but Rossby is very low. So it's very rapidly rotating turbulence hydrodynamically. And also, of course, the magnetic field's generated there. So there are massive MHD effects as well. That's just the current Earth. In the past, early Earth, we had magma ocean, and eventually the mantle started actually solidifying from the middle, and we had a basal magma ocean as well. Those also were settings where you had strong convection but rapid rotation. The Earth was actually rotating more rapidly than by maybe a factor of 2 than it is now. So maybe similar dynamics. And now we have amazing subsurface oceans on a bunch of icy moons. And so we have exo-oceanography, right? And these systems also are probably convecting. Surely there's turbulence. And there's definitely lots of interesting physics going on. There can be melting of this shell. There can be heterogeneous tidal heating. Delightful bodies. Okay. What else is in there? Giant Jupiters, gas giants, Jupiter, Jovian, Saturnian. Fabulous. Good words, people. And that leads us to bodies like this, gas planets. So therein lies Jupiter, roughly gaseous. I think mean density is roughly water, though, if I remember correctly. Nick just mentioned that to me. And one of the things we'll probably hear people talking about are the zonal flows on Jupiter. Paul will be talking about that, Boris Galperin. A bigger gaseous body then would be solar. The sun, we'll have numerous talks on the sun. Outer third of the sun, starting from about 0.7 to 1 in terms of solar radius, is the convection zone. Inside that is a stably stratified radiative zone. This is a nice image from Nick Featherstone on the Coffee's Science Drive Center. Upper right shows the differential rotation or the zonal velocity field. And you see, interestingly, the zonal velocity is roughly constant as a function of latitude, which is very different than what we think is occurring in Jupiter, where we think we have axially aligned zonal motions going down maybe for the first somewhere between 2,000 to 5,000 kilometers. So a thin yet actually relatively deep zonal flow on Jupiter, much deeper in a relative sense on the sun, but it's not axially aligned. So there's definitely some different physics here. And in addition, very strong boundary regions. We have the tachocline at the bottom and the near surface shear layer at the top. And so we don't actually have boundaries so much on the sun, but we have massively important boundary layers. And the interaction of the boundary layers with the bulk convection zone are a huge part of understanding solar dynamics. So we'll hear about that this week. Okay. I mentioned zonal flows. Yes, in all these bodies, we have This was to help me compare that to that. But yes, here are axially aligned zonal flows in a model, not of Jupiter, but of flow inside one of the exo-oceans. So all these tie together, and we should be comparing our predictions in all these bodies. Okay, MHD. When I look at the sun, I think MHD. So I put MHD next. Just briefly, all these systems are MHD systems. Magnetohydrodynamics matters everywhere in the sun. In Jupiter, we'll hear about ways to quench and truncate the depth of the zonal flow on Jupiter. That is almost surely an MHD process. Paula will be talking about that this week. But when I say MHD, well, it applies everywhere. Earth's core, MHD. There was possibly a basal magma ocean dynamo, MHD. How did we find the subsurface oceans on these icy moons? Induction. Again, MHD. So maybe this conference or workshop is focused somewhat on rotation more than on hydrodynamic effects, but everything we're talking about, we should be talking MHD as well. These are truly intertwined globally. All right, MHD. What else is in my, yes. I don't think I put in a slide for this, but I meant to mention too, on all these, a lot of these gaseous bodies, we have vortex crystals and vortex structures at the poles. I think we'll hear about that this week. Exactly. And the other thing I think of when I look at these shells of fluid is I think of confinement. All those images were fluid contained in a spherical shell. But a lot of the work we'll hear this week, especially a lot of the lab work, a lot of DNS, we don't do spherical shells. We'll do convection inside either a box or more likely, more often in a cylinder. And then in addition, we'll hear theoretical work where the fluid is not confined at all. So very different geometries. One is maybe more planet-like. One is more relevant to what we can study most easily in a laboratory setting. And one is a lot like what you see out your window in almost any cloud deck, kind of an infinite plane. So this ties together. This then leads to what are the communities here this week that we're trying to tie together and get to crosstalk. I put turbulence for that, but really it could be turbulence, theory, applied math, call it whatever you will. Maybe for these cylinders, I think maybe that's dominated by what I'd call the fluid physics community. And if we're simply worried about the fluid physics of rotating convection, that is such an elegant, beautiful, simple system. So that's often what's studied. And then we have spherical shells often for the geophysics, stellar physics, solar physics, astrophysics, crowds. So those are the communities we should be trying to get to crosstalk all week long. Let's not assume that we're talking to people who know what the hell we're saying. The person next to you may be actually fairly far apart from wherever you are. That's our job. We're luckily in a small enough crowd. The joy of being in a moderately small workshop, we get to really have time to crosstalk, so let's do it. And in addition to communities, there are methods. Observational methods, we have theory, numerical methods, and laboratory. It's all here today. And so this, in a sense, already is a Venn diagram. We have all these different communities meeting. We're going to jam them together, and do not be shy to be overly explicit to get that crosstalk to occur. All right, so that's what we get out of confinement. And in a way, that's the beauty. We are confined to a nice small space. And so let's really jam ourselves together and create some new structures. All right. Icy gas plasma. Yeah. Icy gas and plasma make me think material properties, right? Icy, those are water-based moons. Gas, maybe those are gas planets. Plasma, the sun of some kind. Stars. And so let's talk for a minute on Prandtl dependence, material property dependent rotating convection. So I'll go right to Prandtl dependent onset of convection. Okay, if the Prandtl number is greater than about 2/3, then rotating convection tends to onset via stationary motions. Upwellings and downwellings that are stationary at onset, beautiful lattice of up and down flows, and the Rayleigh number at which this occurs scales as Ekman to the minus 4/3. So the more rapid the rotation, the higher we have to force it to break kind of the gyroscopic stabilization of the fluid layer. So that goes as Ekman to the minus 4/3, and the horizontal length scale at which this instability occurs goes as Ekman to the 1/3. I mentioned that earlier. So they're getting skinnier and skinnier, and you're needing more and more of a driving force to get this convection to occur. In contrast, if we go below to a low Prandtl number fluid, like a liquid metal or many plasmas, then you can get oscillatory onset. And the oscillatory onset does not depend at all in any way on the viscosity of the fluid. Viscosity is hidden in the Ekman number, but this is called the thermal Ekman number, and it only depends on the thermal diffusivity. That's now the dominant diffusive effect that lets us break the rotational constraint. So it has the same structure, but now Prandtl comes in. And we see that actually that lowers, since Prandtl's low here, we have a lower Rayleigh number there. And here, the length scale now goes as Ekman over Prandtl to the 1/3. Since this is a small number, we get larger scale structures. So we get larger structures that are easier to excite, and they're oscillatory. And so if you look at a time series from a couple of thermistors, you see these gorgeous oscillations right near onset. Okay. One of the big questions, I absolutely love these different modes. How does the turbulence, though, let's say in extreme systems, vary with Prandtl? Does it matter at all? Does it care? We need to know these things because we have rapidly rotating systems with very different Prandtl numbers. Icy moon oceans, Prandtl 7. And then you can go into the interior of the sun. Prandtl's many orders of magnitude less than 1. Do we need to take that into account when we're modeling the physics? Okay, so there's Prandtl. Okay, walls, modes, boundary. Let's do wall modes. So here are in this image from John Chang, this is actually oscillatory modes inside a liquid metal in a cylinder, aspect ratio 2. Yeah, and you can't miss that along the side, there are sidewall boundary attached modes called wall modes. They're precessing retrograde in this case. And in many cases, we find that they're the only mode, right? So this can be very important, these wall modes. And so then we should know how they work. The onset of wall mode convection goes as Ekman to the minus 1. So it's Ekman to the 1/3 easier to excite wall modes than it is to excite bulk modes. So it's often the first convective mode when Prandtl's greater than 1. If Prandtl's less than 1, then the oscillatory mode sometimes will kick in first. So in liquid metals, you can still have oscillations first. In higher Prandtl fluids, wall modes typically show up first. All right, and then if we start going to slender cylinders, which a lot of people are studying, because if we have, let's say, a finite width device, if we want to get more and more extreme, we should make it taller. The Rayleigh number goes as L cubed, right? Ekman goes as 1 over L squared. So if we can change that length scale, we can get more bang for our buck for a given, let's say, experiment or numerical model. Same thing. So then we probably are going to go to low aspect ratio as we try to do more and more extreme experiments. And so if you look at the wall mode onset, and this is mapped out in Jeff Vassel's new paper, I think still in review. This goes as 1 over the aspect ratio, and again, 1 over Ekman. And so it gets a little harder to get wall modes to onset as we go to skinnier and skinnier tanks. And talking to him last week, he pointed out, which I really like, that as we go to skinnier and skinnier cylinders then, and this becomes of order Ekman to the 1/3, then the wall mode onset matches that of the bulk. Why? Because we've gone to a cylinder that's roughly the scale of a bulk mode, right? So that's a really nice asymptote. All right. What do we see in the lab? This is an image from Jula Bate again. This is now sidewall thermometry at the midplane in a tank of liquid metal. Gamma is 1/2, so a somewhat slender cylinder. And we see this beautiful thermal wave propagating retrograde in time all the way across our tank. Very, very coherent. That is a precessing M = 1 wall mode. That's right about twice supercritical, 1.7. If we go to 2.5, the precession speeds up. That drift speeds up a bit, but we still have our M = 1. And if we go to 15 times supercritical, speeds up more. But we never break down the structure. And so we'll hear, I think, a number of talks on wall mode dynamics, the drifting of the wall state, and all the nonlinear dynamics associated with that. Yep, and when I say nonlinear dynamics, the wall modes oftentimes invade, take over the bulk, amongst other things generating zonal flows, sometimes generating large-scale vortices with the same structure as the wall modes. And that leads to the question that really ties between the fluid physics and the geophysics or GAFD communities. When can we apply cylindrical experiments to natural systems? If we're looking for some extended layer dynamics, but it's actually the wall mode that's taken over the whole system, then we better be pretty careful how we go back and forth. And that is definitely, talk about the interplay and separability. That is, for me, huge. That interplay and that separability of bulk versus wall structures is crucial for how we do finite scale numerical and laboratory experiments and talk to theory and talk to stars and planets. Okay. Yeah, so one of the ideas then is, hey, maybe we can truncate the wall modes. And that's an idea from Terry in 2023. Here's their model with nothing on the wall. Here's their sidewall, massive wall mode. That's that structure right there. And when they put a fin, a horizontal fin, on the sidewall, it basically eradicates UZ. It kills the vertical flow. You kill the vertical flow, no wall mode. That holds near onset. But what happens when I go into a lab experiment where I'm far, far beyond onset? Locally, I'll get a wall mode here and here. So then do we add more fins? This is what they consider in their paper too. And again, as we go to really tall tanks, are we going to have 50,000 fins? It's not clear how, one, it's not yet clear that this works in the lab, but then under what range does this valid? The idea is awesome. But what's the best way to do this? And then that leads to the next question. Who am I to eradicate wall modes? Should we even want to? If I'm a fluid physicist, I sure as hell don't want to. These are this is really the newest game in town. These are amazing structures. I didn't believe really that these mattered about 10 years ago. So I said to Bob, I think it was 2015, I was like, yeah, those don't really affect my tanks. And now 10 years later, I'm showing you image going, oh my God, the wall mode signal on the sidewall is King Kong. It's huge. So do we want to remove these? And I even asked, do we want to remove these? Because also, talking to Jeff Vassell last week, he was arguing these are going to show up in spheres. They're going to show up everywhere. They're almost always the first onset mode. When are they showing up in spheres? I don't know. I haven't seen them. But it may well be in extreme systems. They are dominant in both. Okay, wall modes, boundaries. There's more to talk about with boundaries. Yeah, let's talk about heating, driving, tidal. Those words show up. All right, so let's talk about boundary conditions. With uniform boundaries, you might expect everything's boring and simple. It's not, never is. If we even just go to a sphere, we could do this even in a plane layer. It's not boring or simple. But if we do this in a sphere, and make measurements of heat transfer near the equator versus at the poles, then you get two different heat transfer universes. Near the equator, we get this red data, and near the poles, we get radically different data. And so the heat transfer in a rotating spherical system with ideal fixed temperature boundaries is still completely different. There's a regionalization of the physics as you change latitude. The equator's different than the poles. The alignment between gravity and rotation is different. So already there's complexity there. And then if you add in heterogeneous conditions, just a cute lab experiment, hopefully we'll do one or two of these this week. We have evaporative convection in just a little desktop tank of water. There's evaporative convection out here, and then we put in a cold source in the center. So now there's a lateral temperature gradient. And we now have coexistent vertical rotating convective modes. That's the onset scale. That's Ekman to the 1/3. You can see it in the dye. But then we also start getting Rossby radius, deformation radius, baroclinic instabilities moving laterally through the tank. They coexist. And if I'd waited longer to take this image, eventually these started coming back in this region as well. So they literally are coexistent. And so we have multiple modes we have to talk about as we add in heterogeneity in the driving. We can add in melting. That absolutely matters the minute we start talking about, for instance, icy moons. Very nice new paper in Icarus, Gastine and Favier, where they've got rotating convection in a fluid shell underneath a meltable outer material. This shows the melt interface, and you can see it's locked in this case to the structure of the convection. They also show that it starts changing the structure of the convection. So that's really important. I will point out this is at Ekman 10 to the -3. At such a high Ekman number, you only get maybe m = 5 flow. As we go to a planet or a moon, Ekman's maybe 10 to the -12-ish. Well, then instead of m = 5, you'd have maybe m = 10,000. Does that matter anymore? So how do we asymptote this? And what does it mean as we do? Lastly, boundary conditions. I've talked all about thermal, but what if we have topography? What if we have a non-spherical system? Then we can pump in energy mechanically with topographic torques. So if we have something like libration, I think Mikhail Labars will be talking about boundary bulk librational interactions. Here's a movie of particles in a rotating and oscillating, thus librating, spherical cavity, actually ellipsoidal cavity. And as we drive away at this with this sinusoidal forcing, I didn't know it, spent so much time thinking about it today. Oh, this is longer than I thought. I'm gonna be impatient. Very slowly, we pump energy into this flow, and eventually it becomes mechanically destabilized, okay? And so there's an excellent example of boundary bulk interaction. Does not have to be buoyantly driven. Okay, more boundary. But now let's go, we're talking all about the heat flux or the energy coming through the boundary, but we could also do internal heating where we don't put energy in through the boundary. So then we have internal heating. We'll definitely see at least 2 talks on this. One by Basile, where they've very elegantly have figured out how to deposit heat optically directly inside the fluid layer, no boundary layers. That's so wonderful. And in doing so, their data surely argues that they can go right to the asymptotic regime where they find diffusivity-free heat transfer. Another incredibly elegant experiment we'll learn about this week is from Seth Putterman's group. They are doing they are doing a microwave-driven sulfur plasma bulb rotating. This is about 3 centimeters in diameter. And they're creating, arguably, a very, very small stellar system that we will learn about. All right. Okay, I don't know where I am for time, but we've now reached some of the last words that I could get to: gap bridging, extreme predictions, and validation. And so in everything we talk about, fluid physics, turbulence, geo and astrophysics, it's all about making sure we have asymptotically relevant predictions. And so a lot of times we'll be doing experiments down here where the behavior of F is got a lot of curvature to it. What we want to do is get out here to the asymptotic regime where there is no curvature, and then maybe we can extrapolate out to planets. Oftentimes theory is living out here, DNS and lab living typically here. So how do we bridge that gap? What approximations do we have to make? How do we reduce the system in order to, one, make accurate predictions out here, and then how to make accurate models that are living in this world? And how do we know when we're making good predictions? Right, how do these systems behave? How do we reach them? And can we reach them? And honestly, even a few years ago, I would say, no, we can't reach them. Well, we think we can, but we're incredibly optimistic people whenever it's our data. When my experiment's on, it's asymptotic, right? No, I wouldn't have argued that even a few years ago. But there's a lot of data coming out now that seems to be going otherwise. This is a nice study, JFM 2024, Wei Fan. And they're doing spherical shell rotating convection. This is his kind of low Prandtl-ish data set, 1.1.01. And the heat transfer looks like it's following or nearly asymptoting to the diffusivity-free prediction, which is really interesting in that he hasn't deposited heat in internally. He's actually passing it through the boundary layers. That's an actually really interesting result. Similarly, in our lab, Jules Abate has been doing cylinders. This is gamma 2, this is gamma 1/2. And now we're looking at the Reynolds number in the z direction. And she gets this Rossby squared, convective Rossby squared scaling. And if we multiply both sides by Ekman, then that's Rossby versus Rossby squared. So that looks to be following the asymptotic predictions as well. This coefficient matches the theory, or actually the reduced model prediction from Keith Julian, 2012. So this tank is about 10 centimeters, 20 centimeters in diameter by 10 centimeters high. So we're getting to the diffusion-free behaviors in an RBC system in a desktop tank. That's really interesting. And you might say, wait, it's kind of good here. It's a little touchier out here. Yeah, this is the taller tank. And in the taller tank, the wall modes have taken over much more strongly. And so the taller we go in our tank, we thought the taller we go, the more extreme the system, the closer we'll be to asymptopia. No, opposite. The taller the tank we go, the more dominant are the wall modes and the farther we go from the asymptotics. So we actually need wider, not shorter, but wider tanks. Okay, fine. All right, lastly, bridging. When I think of bridging and approximations and reductions, I then think of reduced models. And that leads to the question, under what conditions can we generate elegant reduced models that accurately get all the physics right? It doesn't have to be GAFT. Could be fluid physics too. But I'm often worried about geophysical systems. Here's an image from Thomas Gastin again. And the question is, when can we do local area models? Either in this case, all three of these are in the lab, or numerically local area models, or planar models that get the physics right for these complex systems. And so if we go back again to this study by Gastin and look at the polar data, this is polar heat transfer versus polar supercriticality, and we're comparing DNS, his DNS just measured heat transfer from the pole versus reduced models, again from Julian, and doubly periodic models from Stefan Stellmach. And they're in, I would argue, quantitative agreement. Trends and values. Same thing for the locally measured temperature gradient, axial temperature gradient at the pole. So there can be good agreement between reduced local area models and planar theory and reduced theory. Okay, lastly, reduced theory leads me to Keith. Keith passed away this past April, as Bob mentioned, somewhat as a great surprise to the whole community. I'd like to point out he wrote the proposal that brought us all here. He came here in spring of 22. I think it was 22. Might have been early in 23. No, it was 22. And he was on sabbatical, and then he got here. We were going to write a paper. And of course, I was busy with class. And I was flailing, and it's Keith, he pivoted. He said, oh, we should be back at IPAM. We got to get to IPAM too. I'm starting to write that. And he just sat down. He wrote the first draft, the bulk of it. I would help whenever I could. We brought on Susanna, we brought on Rudy, but Keith did all the heavy lifting because he absolutely believed in bridging all the gaps and building the community. He was amazing, one as an applied mathematician, but two as a leader. And a leader in that he brought everybody together and he tried to make everyone better. And so it's crushing that he's not here in this room today, but in many of these talks, and in my mind, he's still the dominant thought leader, because he is, and he was. And I hope everybody speaking this week will do me a favor, or do everyone a favor, and point out whenever he was important to the work being put out. Doesn't mean he's a co-author, but how did he affect that work? And we should be saying his name when and where it naturally comes up. And if we do that, he'll be sprinkled throughout the week. And we should be remembering him and thinking of his greatness through this week, I hope. And so, yeah, really, those are just a few words, but he ties into almost every word here. So in summation, we have actually a wonderful problem. We have a relatively small meeting, but with an incredibly diverse group, big word cloud. I hope this week we can make as many ties between all these words as possible. And I'm absolutely looking forward to it. I love being at IPAM, and I'm thrilled everybody's here. So thanks a lot.